This video is going to tell you a little bit of background about the critical angle and show you an example. A little bit of background information you need to make sure you know. It's about Snell's law, n1 sine theta 1 equals n2 sine theta 2, and about the index of refraction. You also need to be aware when a wave of electromagnetic radiation, or light in this case, travels from a high index to a low index, it bends away from the normal. When it goes from a low index to a high index of refraction, it goes towards the normal. So let's talk about the critical angle. An infamous, thought extinct, eye laser beam shooting glowfish is down at the bottom in the water, and I've got water underneath and air on top, so I've got a high index to low index, and he's going to shoot a laser beam up. So here's his laser beam going up, and you can see how it bends away from the normal. Remember, the normal is perpendicular to the surface. And then he's going to shoot another laser beam up, and we can see that the laser beam, when it enters the air, refracts. So at this point, the fish can see everything that's in the air. Up here, still seeing everything that's in the air that his light can hit. But there is a point where he'll shoot a ray, and it'll bend away from the normal, because it's going from high index of refraction to low index of refraction. So it'll get to a point where it goes 90 degrees. When the angle of refraction is 90 degrees, the incident angle is said to be at the critical angle. Okay, when the refracted angle is at 90 degrees, the incident angle is the critical angle, and we refer to it as the critical angle. Now, as he keeps shooting his laser beams, he's going to shoot it beyond the critical angle that I've drawn here. And what happens now is, instead of light reflecting, instead of seeing things that are in the air, he now sees things that are underwater. So he sees a reflection of other stuff that's underwater. So basically, when his angle that he's shooting at is inside the critical angle, the light is refracted. At the critical angle, it's refracted exactly 90 degrees. And when it's beyond this critical angle, which is that yellow region, it's reflected. Alright, so let me show you a little image of that. Here we go. So this is an underwater shot, scuba diving, about safety and scuba diving website. And when I look up, what I can see is kind of a circle. It's not real clear because the water above is kind of choppy, but basically I'm seeing this circle up here. Everything inside the circle is refracted light from above the surface of the water. Everything outside the circle, and there is stuff outside the circle because it's kind of a square cut, everything outside the circle is a reflection from the bottom of the water that I'm sitting in. So it's dark because there's no lights reaching it. That's why it's dark like that. Okay, so here's Snell's law in the critical angle example. The question is, what does the light ray reflect or refract, and at what angle? Or will the incident light ray reflect or refract, and at what angle? So I've got the two substances. I'm going from high index refraction to low index refraction. So the light should bend, well, you can guess, away or towards the normal. In this case, it should be bending away from the normal as it goes to a lower index of refraction. And my task is to find that light ray, if it'll reflect or refract. So here's my strategy. I'm going to find the critical angle. If the 28 degrees of the incident ray is greater than this angle, then I know it's reflected. If the 28 degrees is less than the critical angle, it's refracted. And that tells me how to solve for the problem. Alright, so let's find the critical angle first. I'll use Snell's law, n1 sine theta 1 equals n2 sine theta 2. And n1, I'm going to, so let's go with the incident side. So 3.4 sine theta c for the critical angle. And I know it's a critical angle because I am determining that the refracted light is going to bend 90 degrees. And the refracted light is going to be on the lower index of refraction's side. So 3.1 sine theta critical angle is equal to 2.6 sine 90 degrees. This means the critical angle is going to be at 49.88 degrees. That's great. So now I know the breakpoint between refraction and reflection. And since my angle is 28 degrees and it's less than 49.88 degrees, the light ray is going to be refracted. So I'll put my numbers in Snell's law. So n1 sine theta 2 equals n2 sine theta 2. Putting my numbers in, 2.6 sine sine theta equals 3.4 sine 28 degrees. So the left side is the low index refraction side. The right side in this case is the high index refraction, or the incident light ray side. And that gives me an angle of 37.9 degrees. So that's the refracted light angle, 37.9 degrees.